Okay, so thanks very much for having me as a speaker today. I'm going to give you a talk titled The Secrets of Our Universe, which is a little bit about the work I'm involved in here at Cern in Geneva. I'm an assistant professor from University in Toronto, so I'll give a brief introduction and then afterwards we can chat about whatever questions you may have. So let me start off with a quote that Michelson said in 1903 that said, "The more important fundamental laws and facts of physical sciences have all been discovered." And of course, in 1903, Michelson had every reason to think this, because we had gone from 400 BC, thinking the world was made of earth, fire, air, and water, to 1870, where we had characterized the entire periodic table, and we thought after that physics was done. Of course, physics wasn't done, because in 1910 what we discovered was that each element of the periodic table was actually made of even smaller particles called atoms. And those atoms looked something like this on the left-hand side. They had a nucleus inside and they had electrons orbiting it. Then in 1930 we found out that wasn't the end of the story. This tiny nucleus inside was made of even smaller particles. Those smaller particles in the 1960s became known as protons and neutrons. And we discovered that the protons and neutrons themselves had substructure. They were actually made of particles called quarks. And today we understand that there are many quarks. We have 6 different types of quarks, which are these particles that are shown in the purple. And we not only have the lepton, which orbited the original atom, but we have 6 particles that are like the lepton. We have another muon, a tau, and what we call neutrinos, which are very light particles that barely interact with anything. So our understanding of what matter is made of came a long way in that short amount of time. Our understanding of how forces in the universe also drastically revolutionized. So in 1660, we knew about gravity. Then in 1860, we found out about magnetism and the electromagnetic force, which is responsible for light and magnetism. Then in 1970, we discovered what's called the strong force. And the strong force is responsible for keeping these really small particles we called quarks bound together inside our protons and neutrons that make up the atom. At the same time, we found about something called the weak force. And the weak force is something that is responsible for the interactions in our sun. And today we know that each of these forces has an associated particle that mediates it. So we have the gluon that mediates the strong force, the photon that mediates this electromagnetic force, so electricity and light, and the Z and W bosons, the ones down here that mediate this weak force that's responsible for the interactions within the sun. So this is how we came to know what is today known as the Standard Model, which is the most accurate theory that predicts what matter and forces in the universe are made of. And this is what the Standard Model looks like. It consists of these 6 particles that I called quarks. Okay, we have an up quark, a down quark, charm, strange, top and bottom. They have a bit of funny names, but that's what they are. We have 6 particles called leptons. We have an electron and an associated neutrino. A muon and its neutrino, a tau and its neutrino. We have these red particles, which I just mentioned are the force carriers. They're responsible for the forces I discussed. And up until 2012, the Standard Model of particle physics was incomplete because it did not explain how all these various particles got their masses. And then in 2012 at Cern, we found the last particle of the Standard Model, which we call the Higgs boson. And this completed our understanding of the Standard Model. Notice one thing, that out of the forces I mentioned, gravity is currently not included in the Standard Model, which is a huge problem for this model. Now, I mentioned that we found the Higgs boson particle here at Cern, and finding it was a lot of hard work. So I just want to give you an emphasis of what finding it actually means. So here at Cern, we collide particles with each other. And if you look at this plot here, this is the energy on the axis here at which we collide the particles. So the Large Hadron Collider collides particles at 14 tera electrovolts, which is represented by this green line. Okay? So to give you an idea, when you're colliding particles at this energy, we expect about 10 to the 8 events to be produced every second. Out of those 10 to the 8 events, only 10 to the -2 events per minute per second or 10 events per minute are going to be the Higgs boson. So in order to find the Higgs boson, we have to get rid of 10 to the 10 events. So 10 orders of magnitude we have to get rid of in order to get to the Higgs boson. We have to throw out this much garbage in terms of data in order to discover our Higgs boson. And this really is like looking for a needle in a haystack. So our standard model of particle physics we thought was pretty complete theory. However, as Albert Einstein said, the more I learn, the more I realize how much I don't know. So what don't we know? What doesn't the standard model particle physics address? Well, first, there's what's known as the hierarchy problem. What is the hierarchy problem? So I mentioned that we have this particle that's called the Higgs that gives other particles their mass. Now, we calculate the Higgs using what's called the quantum field theory. So let's say we are trying to calculate the mass of the Higgs. So we do that by taking the mass of the Higgs in a vacuum, which is this blue term, plus a mass of the Higgs that is predicted by quantum mechanics. Now, the interesting thing about the Higgs particle is it can turn into a bunch of other particles and then back into itself. So that's represented by this diagram that I'm circling. So this process of the Higgs particle turning into other particles and then back into itself is an effect of quantum mechanics. And it turns out when we're trying to calculate the mass of the Higgs particle, this term from quantum mechanics is very, very large. It blows up to infinity. So we're left with a bit of a conundrum here, because when we calculate the mass of the Higgs in a vacuum, we have a really big number here. Then when we take the quantum mechanic mass, we have another really big number here. But then when we measure the mass of the Higgs particle, we have a really small number. The small number is only 125 giga-electron volts. What does this mean? That means that this first really big number, it's 38 digit long. And the second really big number, it's another 38 digits long. They have to cancel each other very precisely in order to give us this very light Higgs mass. Okay, so that's like having one 38 digit number and another 38 digit number and 35 of those digits being completely identical and only the last 5 digits being different. And that's how you get a really light Higgs mass. So the probability of that happening is really, really, really small. Imagine you have two 38 digit numbers and 35 of those digits are going to be the same. If you just picked any random 38 digit number, this probability is almost impossible. So as I think a theorist once put it, the Higgs has a snowball's chance in hell of having a mass in that ballpark. And that's a very literal analogy. That is as if you were in a fiery place and all the cold particles in that fiery place aggregated in one part to make a snowball. It's a really low chance. So that's what's known as the hierarchy problem in the standard model, and it's a really big issue that we have to address. What are some other deficiencies of the standard model? Well, one of them is we don't know what dark matter is. Now, we know it exists, and I'll tell you how we know it exists. Let me start off with an analogy, okay? Imagine you have 2 buckets of water, and in each of those buckets you have some balls. So in the left bucket you have purple balls, in the right bucket you have some red balls, and you throw those buckets of waters at each other. What do you expect to happen? Well, you expect the balls to fly through each other. So you expect these purple balls to come on this side, the red balls to come on this side, and you expect the water to linger in the middle. And analogous things we can expect from when galaxies collide. So we've now observed pictures of 2 galaxy collisions. So one on the left, one on the right. And when these 2 galaxies collide, this is the resulting image. Okay, so the stars in that galaxy can be thought of as the balls. And the stars pass right through each other, so they end up on the opposite sides. Now, the gas in the plasma, which makes up more than 90% of the mass in the galaxy, can be thought of as the water. So we expect that the gas in the plasma, which is represented by these purple and blue halos seen by X-ray telescopes, we expect that as these big gas and plasma collide, that they're going to linger in the center like the water lingered. And we expect that because we previously thought most of the mass is in this gas and plasma, that most of the mass is going to be located in these purple and pink regions, which is where this gas is. But when we found a completely different way to infer where the mass in this galaxy collision was actually located, we discovered it was not at all in this gas and plasma, which is analogous to this water, where we thought it would be located. So, where we found the actual mass in these galaxies was a bit surprising. First, let me talk about how we inferred where the mass was. We looked at an effect that's called gravitational lensing. Now, what is gravitational lensing? Imagine you have a star far out in the galaxy. So this is your star, and we're observing this star from Earth. So here where I have my mouse is where Earth is. So imagine you have a big, really heavy object between the star and the Earth. Now, because this object is big and heavy, it will warp space around it. It'll create like a dent in the fabric of space. You can think of it as putting a bowling ball on a mattress. You're going to have a dip in it. And then as the light travels from this star around this heavy object and us to Earth, the light is going to bend because the space around this heavy object is bent. So the light is going to bend around all sides of the object. And when we look at this star, we won't see a star. We'll see this picture here, which is a star and a halo around this star. And the halo is the result from light having been bent by this heavy object. So when we infer where the actual mass is in these galaxy collision, what we get is this picture on the lower right-hand side. So previously we thought the mass would be in these yellow and blue spots where all the gas and plasma was. But when we use this technique to infer the mass, we see the mass is actually located in these green circles. And what does that tell us? That tells us that when these galaxies collided, it's true that the stars flew right past each other. It's true that the gas lingered in the middle, but previously we thought most of the mass was in the gas, lingering in the middle. And what we found out is that most of the mass is actually on the outside here, which means the mass, most of the mass of these galaxies just went right through each other and barely interacted. So you have these two big galaxies, they collide, their heavy gases linger in the middle, but some mysterious objects, some mysterious type of matter passes right through to each other. And this mysterious matter came to be known as dark matter. And because it makes up most of the matter in the universe, it makes up about 26% of matter in the universe, it became very interesting to us. And we have no idea what this stuff is made of. So everything in the universe, the stars, the planets, everything that we know of is only 4% of the universe. This fancy model of particle physics that you call the standard model, that's just 4% of the universe. The rest of the matter, the other 26%, is what's called dark matter. And we have no idea what this stuff is made of. So one of the goals that we want to address next is what this dark matter stuff is. Now, this 30% is only 30% of the pie. The other 70% of stuff in the universe is even a more mysterious substance, which we call dark energy. And I won't get into what dark energy is, but it's another thing that is a big unknown to us that the standard model doesn't address. So 4% of the universe we understand using this standard model. The other 26% is dark matter. We have no idea what that stuff is. Another 70% is dark energy. We have no idea what that stuff is. And those questions are things that we want to address in the future. Other things we want to address is why these very light particles, which we call neutrinos, have mass. The standard model tells us that they should not, but experimental evidence tells us they do. So that's another problem with this standard model of particle physics that we have. Another problem is in the universe we have matter and we have antimatter. And when matter and antimatter collide, they annihilate and they leave nothing behind. And when we're looking at the universe, all we see is matter. And we're wondering where is the missing antimatter. In the Big Bang, we should have had equal amounts of matter and antimatter created. So why do we have all this matter left over and no antimatter around us? So these are other questions that we want to address that the standard model doesn't tell us about. And we can address those things in two ways. We can either look for deviations from the standard model by measuring Higgs properties, because the Higgs is our latest discovered particle and our most mysterious one. Or we can look for beyond standard model theories that could possibly explain some of these anomalies. So, as William Deming, I think, said, in God we trust, all others must bring data. So, how do we get the data in order to address some of these questions of the standard model? Well, we just need something that resembles a time machine and a magnifying glass. So, what do I mean by that? When the Big Bang was created, a whole bunch of particles that I just talked about, these quarks, these leptons, they all existed freely in what's called a quark-gluon plasma. And as the universe cooled, these particles started to join each other, and they made atoms. And then those atoms made bigger particles. And then these bigger particles made molecules, molecules made galaxies and stars, and so on and so forth. So as the universe cooled, all these particles got together and they made bigger and bigger objects. So we need a time machine in order to go back to when the universe was very young, when it was only 10 to the negative 10 seconds old. And we want to look at when these particles of the standard model existed as independent entities, when they were just free to roam around. And then we want to have a very close look with something that resembles a magnifying glass at these individual particles. So what will serve as this metaphorical time machine and magnifying glass is the Large Hadron Collider at Cern. So this machine is used to smash particles into each other at very high energies so that we have all these individual standard model particles released and we can analyze them using very big detectors. So this is what the Large Hadron Collider looks like. It's a 27-kilometer tunnel. It's located on the French-Swiss border. And it's a ring between 100 and 175 meters underground. It's a giant tunnel and it collides protons in both directions. And we have 4 different points around this ring, which are labeled here Atlas, Alice, LHCb, and CMS. And each of these different points is a different experiment. It's a different metaphorical magnifying glass that looks at the collisions created by the Large Hadron Collider to get to the information about these particles. Now, the Large Hadron Collider doesn't just take one proton and another proton and collide it together. It actually takes 10 to the 11 protons in one bunch and 10 to the 11 protons in another bunch, and it collides these things every 25 nanoseconds. That means every 25 nanoseconds, we have a huge number of collisions and interactions. So our job is much harder than just looking for a needle in a haystack. It actually comes, given that how many overlapping collisions we have every 25 nanosecond, our job is akin to looking for a needle in a haystack in a battlefield, basically, because our interesting physics events are so rare. Just to give you some numbers, the Large Hadron Collider gives us a 40 megahertz collision rate, but we can only save 1 kilohertz in our final data output. So I mentioned we have 4 different types of experiments. And the one I work for is called Atlas. So the Atlas is located on one part of the LHC. This is sort of a zoom in of the Atlas detector. It's a schematic representation. It's huge. So I've put a little person here to demonstrate to you how big the Atlas detector is compared to a person. And it's like a giant fancy camera. It's 46 meters in length, it's 25 meters in diameter, and it weighs over 7 tons. The innermost part of that Atlas is what we call the inner detector. Excuse me. And I mentioned that the inner detector, it tracks all these. I mentioned there's a lot of overlapping collisions. So every 25 nanoseconds, we have so many collisions that one photograph from the Atlas detector looks something like this. It's very busy. These are all different interactions from these standard model particles. So how does the Atlas detector work? Well, imagine that this here is a cross-sectional view of the Atlas detector. So you just cut the detector in half and you look at it from a circular point of view. So basically how it works is each of these different colors represents a different technology, and each of these different technologies is meant to detect a different type of standard model particle. So let me go through this briefly. We have the innermost detector. The innermost detector is just basically responsible for gathering information about the momentum of all the particles. Then we have this red layer, which is the electromagnetic calorimeter. The electromagnetic calorimeter detects these particles in the standard model. It's called the photons and the electron. Then we have what's known as the Hydronic Calorimeter. That's this blue layer. And the Hydronic Calorimeter detects these particles that I called earlier, these purple ones called quarks. And also the gluon, because the gluon keeps quarks together in tightly bound. I mentioned that quarks, they don't like to exist independently. As soon as they're released in the collisions, they recombine with other quarks very quickly. They glue together because they don't like to be alone. And this blue layer, which we call the Hydronic Calorimeter, basically detects these quarks that are glued together. And finally, this green layer, which is the outermost layer, it's called the muon detector, and it detects this type of standard model particle, the muons. Now, these green particles called the neutrinos, they can't directly be detected. They escape the detector because they very, very lightly interact with our regular matter, but we can infer their presence. And the way that we prefer their presence is basically by using conservation of energy type of arguments, which I won't get into now, but if you're interested at the end, I can talk about what that is. Then we have more complicated particles. So the remaining particles, the Higgs boson, the ZW boson, the tau, these are all quite big particles, and they decay right away to other smaller particles, and we can infer their presence as well. So this is basically how this how our camera builds a picture of all of the particles in the event. Each layer, as I said, is responsible for detecting, has a different technology, and is responsible for detecting a certain type of particle. So here are some pictures of the Atlas detector. So the very top one here is, again, this cross-sectional view. So it's a bit hard to see, but you can see a person that I'm pointing to with a mouse. So it shows you a fraction of the scale. So this is actually just half of the detector. It's still even much bigger than this, but you can't get it all on the camera. And you can see sort of the different layers that I talked about. This bottom picture also shows the different layers that I talked about. We don't have a person for reference in this. No, we do. This tiny person back here shows you a reference of how big this detector was, and you can roughly see these different layers that I described that correspond to different types of detector technologies. And the picture on the right hand side, again, it's similar. So you can see the little people here, and you can see their little helmets. And you can see how big the detector is in relation to these. So this layer out here is the outermost layer. It's this muon layer that I discussed. So I mentioned the Atlas detector takes photographs. So these are some examples of the types of photographs and pictures the Atlas detector takes. So you can see, you know, we have the detector, and then when particles collide, they leave these energy deposits, which are represented by these little squares or by these straight lines. And by analyzing millions and millions and millions of these photographs, but not by eye, of course, using statistical frameworks, we can decide which photographs we're not interested in, which ones are just standard model processes that we know exist, and which could be more interesting, like the Higgs boson particle, or other exotic particles that could explain dark matter, or that could explain this hierarchy problem that I mentioned. Okay, so let me just say a few more words about the future of the LHC and Atlas. So this is us in the control room. Now we're in the process of trying to upgrade the Atlas and LHC technology to be able to run longer and to be able to be more resistant to even higher energies. So right now, this is sort of the timeline of the LHC. So we had what was called Run 1, where we gathered a bunch of data. Then we had a shutdown in 2013 and 2014 to update the LHC and Atlas a little bit. And then we ran again from 2015 to 2018 during what was called Run 2. Okay, and then based on this Run 2, we're still analyzing this data. Back here in 2012, we had already discovered the Higgs based on the initial data we got. We're still in the process of analyzing this Run 2 data, and right now we're in 2019, 2022, where we're upgrading more the Atlas detector and the LHC, and we will start, this schedule is a bit outdated now, but we will start again next year in 2022 with what is called Run 3 and try to collect even more data in order to describe, to try to get answers to some of the problems that I discussed. So I think that about summarizes it as sort of a brief introduction. So I'm happy to take any questions people might have about the research or anything else.
So thank you. Very exciting. This is great, Nina. So you have one question. So do you basically so you have this period of collisions and collecting data, and then once data is saved, so you do your research basically by searching and mining through this data, and so I'm interested. So is that so that sounds very exciting also from a computer science point of view, because I assume you are using some statistical algorithms to you cannot manually look through that, but actually to search through these patterns and similar. Is that correct?
Yeah. So let me actually just give you some numbers as to how much data we're actually need to sort through. First, we have a multi-step approach of data reduction. There's no way we could save all the data that we produce, because it's like a 40 megahertz rate. It's I forget how many terabytes in what fraction of time, but it's a lot. So we have what's called a trigger system to reduce the data as we're taking it. So this is sort of an inside picture of the Atlas detector. So the very first step, when we take the data, we build a very blurry picture of the detector, and this is made just using some electronics on the detector. So we have just a very blurry picture of where roughly the energy deposits are, and we very quickly analyze this as we're taking the data on the detector electronics, and if we find that these energy deposits are in interesting places, we keep the event. So this happens at a 40 megahertz rate. So we reduce the data from 40 megahertz to 10 kilohertz in about 2.5 microseconds. 100 kilohertz is still too much data to take. So we need to further reduce this to 1 kilohertz. And the next thing we do is then we look at sort of where the high energy deposits are in the detector, and we narrow in on those. So those are represented by these white cones, and we build a fine, high resolution picture of that data. And this is done at the software level, not at the hardware electronics level. Okay, and then if we look at these areas, these interesting areas of the detector, and we say, oh yeah, this is an interesting event, only then we build the full resolution picture of the event, because we can only save 1 kilohertz to tape. And this building is done in software at what we call the higher level trigger. So this is the final stuff that we save. So we take data at 1 kilohertz, and we have to quickly reduce it using a combination of hardware and software to 1 kilohertz. In the end, we save 1 kilohertz to tape, and we have giant computing farms all around the world. It's sort of a distributed system. We call it the grid. And it's saved. We have tier 1, tier 2, tier 3 sites. So a lot of this data is saved at tier 1 sites, which are giant computing centers around the world. There's backups at tier 2 sites, and then tier 3 sites we use for data analysis. So when we're analyzing this data, we're not just working on data on our computer. We're working on data on our computer that's accessing these different tier data collection centers. And we're not just running the algorithms and statistical analysis on our computers. We're sending what's called jobs to the grid. It's sort of like a cloud computing framework. So I tell my computer please find me a computer that is free in the world that can analyze this data. So then I send this command, and then it's like a distributed system that looks for a bunch of free computers to perform the data analysis, and those free computers then access the data that is stored from the tier 1 sites. So the World Wide Web was actually invented at Cern because it was a way for physicists to be able to analyze what was then considered large amounts of data. And this is sort of the next step. This is what's called the grid. It's similar to cloud computing, but not quite.
Yeah. Well, which language do you use to write these programs, or do you know?
Yeah, we use C++. We use Python. A lot of we have our own software as well. They're like giant software frameworks. The Atlas collaboration alone is 3,000 people. And for the data analysis, we have a whole bunch of different big frameworks that are mostly written in C++ and Python. But they're a bit convoluted software frameworks because there's lots of different steps of this data analysis. It's sort of difficult for a physicist to sit down and to write their own code and just look at the data that is saved somewhere, because there's so many layers of data analysis that you need these giant convoluted frameworks to analyze them.
Yeah, great. Thank you. Fascinating.
On more practical note, did you have to learn, obviously you have to learn those frameworks, but did you have to learn programming languages as well?
Yeah, but physicists, we don't really learn to program. We learn pattern recognition and copy and paste. So if it can be called programming, computer scientists would get very frustrated with our code. But yeah, we all know how to write a certain amount of it, and a lot of it is for loops inside each other, infinite for loops inside each other. So yeah, we have to learn it, but it's not elegant.
What has helped you to get there, and what advice would you have for others who want to set off in a similar direction?
Yeah, I mean, I think my life philosophy is I guess be annoying. I don't know. When I was doing my undergraduate, I was at the University of Waterloo, and we had this what was called a cooperative education program, and we had work terms, and then we had study terms, and then during all my work terms, we had these standard jobs that we would look through our university website, and they were always kind of boring. So what I would do is I would just go to the websites of international universities, and I would just look for where interesting research was being done, and I would email all those professors, and you would get, one reply out of 100, but it was just persistently annoying everybody until you found one research professor that was willing to fly you to a research lab and host you for the summer so you can learn more about the subject. And this worked out really well. Doing this, me and actually my sisters as well, we managed to do most of our university internships at broad and interesting labs for very little money, but the experience is definitely worth it because you can, you can go to a lab for the summer. You can see if you like a particular type of research. You can get exposure to higher level areas of science that you wouldn't otherwise with your university and the university jobs you have, or with summer jobs you might have. So I would just say, yeah, don't be too shy to and just be persistent and annoying and trying to dig out things that are interesting for you. And trying to bug people that might help you along the way, because if 99 won't, one will, and there'll be all the difference. So yeah. I'll give you an example. Actually, another one. So when I was looking for my PhD advisor, I wasn't looking for a PhD advisor. I was doing one of these internships in British Columbia in another lab, and I was sitting at home on the couch, and I was watching a documentary about Cern, and I saw a professor talking about Cern, and I sent him an email saying, I saw you on TV, can I come to Cern? That was basically it, and he said yes, and that's how I did my first undergraduate internship, and I came to Cern, and then he became my PhD advisor, and now I'm working for the same university and for the same institute as him. So
think a great point now when you look back, you contact 100 people, 99 say no. And at the time that could be, difficult, all that rejection, like 99 people didn't want me. But now when you look back, it really doesn't matter.
I never looked at it as hard rejection. I was like, okay, fine. It's not, it doesn't really hit close to the heart. It's okay, you don't have the money, whatever. Somebody will. Or because you're not good enough, which is also fine. You get better then.
Yeah, Nina, I was just wondering, why don't you tell us a bit about Serbia's involvement at CERN? Because it's a pretty interesting backstory, and as one of the founding countries, and since this is the Global Serbia Network, maybe you could talk about that. It's pretty interesting.
Yeah, so actually CERN was founded, so they started construction in the 1950s. I think there were only 12 founding members at the time. And one of them was indeed former Yugoslavia. So it was a few European countries, and Yugoslavia was really was one of the founding members, which was pretty cool back in the 50s. So CERN started back in the 50s, and then since then they've found a lot of standard model particles. Like in the 80s, they discovered these WZ bosons for which they received the Nobel Prize. In 2012, we discovered the Higgs boson, for which the Nobel Prize was received, and along the way there were a lot of different discoveries. So yeah, Yugoslavia was one of the founding nations, and they put up a lot of the initial money. Then in around the 90s, it's a bit of a dark history, I would say, on CERN's spot. Serbia was kicked out for about 2 years when NATO bombed Serbia. Which is unfortunate, because when CERN was founded, the entire principle was that science doesn't know boundaries. Science and the search for truth and the search for knowledge should not be bogged down by the political situation in the world. The idea of a bunch of scientists getting together and searching for things that are fundamental to the universe should not have any implications on political situations. So it's the first time that a country was ever kicked out, and basically Serbia had a lot of open lab space, and overnight they were just told to leave. And a lot of my colleagues now who were there at the time, they just basically had to pack up all their stuff and leave overnight, and they weren't allowed to come back for 2 years. And CERN, I don't think. This was there was a push from I guess the political side, from some countries and from the political side, to kick Serbia out, and then they were accepted back in I think, I don't know, 2000 or 1998, something around that line. And then they came back. They got back to their research groups. They became involved in various experiments again, and then just last year or 2 years ago, they became again what's called a member state. So a member state is one of these, I guess, main members of CERN. They pay a certain amount of membership fees, and now, along with other European countries, they have this member state status, and they contribute to a lot of the different hardware projects. They have quite a few students. We have quite a big Serbian community here. When we get together for lunch, there's up to 20 of us, which doesn't sound like a lot, but for a small country, it's a decent amount. That's, I think, only a fraction of the people that are there. But yeah, so now it's member state status again, and there's various contributions to hardware. I can't get into the hardware contributions because I didn't describe the hardware in enough detail.
Have you ever felt discriminated based on your ethnicity or maybe due to gender?
No, I mean, I think I don't know. I didn't. I love it. All the guys I work with are great. Everybody's. I think discrimination is one of those things you'll always find when you look for. So I have friends that claim they've seen it in places that I would not have seen it at all. I really think, especially today, in my field of work, you have to look really hard to find it, even though it might not exist. So yeah, no, I think I haven't experienced anything like that.
Yeah, that's great. Yeah, as you say, that push at CERN was probably political, not maybe even coming from people from CERN. I bet colleagues were feeling bad what was happening.
But that actually, sorry, I should say that was before my time, right? Those people they were kicked out for being Serbian. that they were, and it was the political push was from scientists inside CERN that were of nations that were doing the bombing. So that was that they felt it, but okay,
Yeah,
I joined in 2015, which is 15 years later,
Later,
yeah.
yeah.
2012 or something. No, 2011. So 10 years later, by which time people had forgotten or didn't care.
So, do you think there are any like common misconceptions when it comes to physics?
Yeah, I think so. I think this is true of science in general, of physics as well. So physics is one of the, I would say, there's a tendency for people to say the science says, the experts say, as if science was a one consensus and there was nothing beyond it. And I think that's a really bad way of looking at science, because I hope that I've managed to show you that every time in science we thought we knew something, our knowledge was turned upside down on its head and we discovered much more. And now in physics, which I think I consider to be one of the most fundamental sciences because it really deals with the most fundamental constituents of the universe, and it's really a science that deals with particles in a vacuum. We only understand 4% of the universe, and very, very badly. So the other 96%, we have no idea what it is. So there's a tendency in science and even in physics to be like, oh, the science says, the science knows. But when you look at the global picture, the science knows very little. So anything we can say about what science knows is just at that given time, and we always have to keep in mind that it should always be questioned. It can always be flipped upside its head, and it most definitely will be, because we know so little. It will most definitely be flipped upside the head. So I just don't think by the time the science gets to the public should be referencing the science as if it's an absolute. They have to keep in mind that it's the best knowledge we have so far, but tomorrow it can be flipped upside on its head. So I'll give you an example. A few centuries ago, we were convinced, and you can find old textbooks, not even a few centuries, like 150, 200 years ago, that something called ether permeated all of space. Ether was just this magical substance that was everywhere in the universe. And things were referred to, maybe you've heard the expressions into the ether. That's because physicists thought there was an ether, which was some sort of stuff that was out there in the universe. And then one guy did one experiment and said, actually, there's no such thing as ether. And overnight, a theory that was, the leading theory of there's this jelly-like stuff in the universe, ether, was flipped on its head just by one single experiment. And the next day, the textbooks just had to be like, oh, yeah, no more ether. So I think that would be the biggest misconception. Science is continuously evolving. There's no consensus in science because there's always experts, doctors, whatever, PhD people that are constantly debating, constantly contradicting each other. And yeah, you just got to keep in mind that it's an evolving field with no real permanent consensus, just the best knowledge at the time that is hotly debated, and that might change tomorrow.
How do you keep yourself and your team on track?
Well, I mean, this depends. I think we regularly, so at CERN, where half the countries are working at CERN, and we always have to be just in constant communication. So when it comes to, the same thing applies to like my students, my postdocs, as well as people that I work with in Japan and in the United States and in Africa. We always just have to be in constant communication, constantly meeting, try to set goals, try to set priorities, because everybody's so dispersed. There's sometimes a feeling that people are forgotten about. So it's important we basically keep regular communication to have people know that their work does matter, because that's when they'll have initiative to do more work. So yeah, just I would say regular checkups, goals, and trying to follow up on what people are doing to make sure that they keep the incentive to keep working, especially during lockdowns and things like this.
Do you have any final advice for young, aspiring minds who want to maybe get into physics?
I don't have any. I mean, I would say I don't have any. Yeah, I would just say, if you like something, be persistent, stick through it.